My previous video showed how we retrieve expected shortfall under the simplest possible discrete case. That was a simple historical simulation, but that was discrete. In this video, I'm going to review expected shortfall when the distribution is continuous. Specifically, I'll use the normal distribution, but you'll see when we look at the code in particular, because I'll show you the code version, that we can substitute other parametric or analytical distributions for that. So we'll look at here this continuous distribution version of the expected shortfall, but I'm also going to put it in context of explain how it's a version of the general risk measure that is coherent because it is spectral, and I'll show you why var is not coherent because it's not spectral, despite the fact that it is also a special case of the general risk measure. Then I'll show you how, or I'll replicate Dowd's illustrations for how we approximate this expected shortfall by selecting a number of slices in our tail distribution. I'll show you that in Excel, but then I'll shift over to R code where I've written code that will give us a much more flexible way of modeling the expected shortfall approximation in the case of these continuous or parametric distributions. So quite a bit of theory, but then some code that I hope is interesting and sheds some light on this very important measure of expected shortfall. So here we have Dowd's general risk measure denoted by capital M, and I would emphasize the word general because this is really zooming back to the generalized version. And it's just a weighted average, really. You might recall from calculus, if we want to take the weighted average of a function, it's going to be the integral of x, f of x, d of x. Well, that's effectively what we have here. For x, we have the quantile. So this general risk measure is a weighted average of the quantile. And instead of f of x here, we have here this, notice it's a function. That's Greek phi. This is the risk aversion function. So that's why it's general, because we can have any function here in this general risk measure. And that's why also this general risk measure encompasses both value at risk and expected shortfall, simply because they have different risk aversion functions. So if I think about here something like a normal distribution, and I want to look at the 95% confident quantile, we know that's 1.645 approximately, meaning 95% of that area under this normal curve, or standard normal, I should say, is to the left of this quantile. The expected shortfall is shown here, and it's a special case of the general risk measure because it has a certain risk aversion function, and you can see, which is again is a way of weighting, is a function for weighting the quantiles. And so here is the risk aversion function for the expected shortfall. And it's saying that if the probability is less than the confidence level, the weight is 0. In this case, if we're to the left of 95% confidence, we're getting a weight of 0. And when we hit 95% or greater, when we're in that lost tail, we're going to have this weight here, which is going to be, in this case, 1 divided by 5%, or 20. So the weight is constant, but this is consistent with, or really this is the implementation of expected shortfall as a conditional average. We're taking the weighted average, conditional on being located in the tail, the weighted average of this lost tail. But each quantile, this is a constant, each quantile is getting equal weight. VAR is a special case also. It's just a little different. If the probability is n equal to alpha, we're getting 0. In this case, n equal. And if the probability is equal to alpha, then we're getting all of the weight. So VAR, in this case here, we say var is a quantile, and we could be more technical if we want to look at it through the lens of the general risk measure and saying it's a general risk measure where none of the quantiles above 95% are getting any weight, and we're getting all of the weight on this one quantile, so we're just really retrieving that quantile. Okay, so if you're with me so far, then the next sort of tricky concept relates to coherent risk measure, and this gets very confusing. I admit, when I first studied this, I thought this was the coherent risk measure. That's not the case, because I've already said that we can see that depending on the weighting scheme, VARs, which is pretty draconian, expected shortfall, which has equal weighting, conditional on being the tail, both of these are special cases of the general risk measure. So both VAR and both expected shortfall are special cases of the general risk measure. However, then we have a different idea that says coherent. Is a risk measure coherent? You probably know that expected shortfall is coherent. Value at risk famously or notoriously is not coherent. Well, what measures are coherent? Well, spectral risk measures are coherent. So now I'm going to say we're interested in spectral risk measures because they are necessarily coherent. And now, what's the condition for spectral? There are three conditions: non-negativity, weak normalization, and weakly increasing. So I'm not going to worry now about non-negative and normalization because they're really not important. What matters is this condition of weakly increasing. And so, well, what's the idea with weakly increasing? Well, that's pretty straightforward. That means this weight is increasing as the probability increases. So if we take that distribution here and look at the tail, we want the weights to be increasing as we move further into the tail, or the weakly really means equal to, as the probability increase, the weight is greater than or equal to. So the equal to part of weakly increasing is satisfied expected shortfall, right? These weights, in other words, they at least don't decrease. They are at least constant. Later, Dowd shows a variation here on this risk function where the weights are increasing, which is more consistent with the risk aversion concept. But as long as the weights are greater than or equal to, then we have weakly increasing. Expected shortfall weights being constant are equal to. So expected shortfall is a version of this general risk measure that satisfies the conditions of being spectral. So to recap, both VAR and expected shortfall are versions of the general risk measure with different risk aversion weighting schemes, where expected shortfall is the only one of them that is spectral because its weighting scheme is weakly increasing, right? Expected shortfall is both general and spectral. VAR is a version of general. VAR is not spectral. Its weight is not weakly increasing, and so it is not coherent. And again, VAR's not weakly increasing because we have all the weight here. We go to higher probabilities, and then we have zero weights. It drops off, and that just intuitively does not match our risk aversion. So table 3.1, using the normal distribution, estimates the expected shortfall as a weighted average of the tail VARs. And so this is a simple idea where we just select the number of slices that we want in the tail. This is going to be for a 95% confident VAR. The n value is 10, meaning there are 9 slices. So we slice this into 10 region with 9 values here. 95.5% increment by 0.5%, and at each confidence level here, I'm just using norm SINV to retrieve the quantile that's associated with this confidence level or probability level, if you like. That's a P value. So for each confidence level, I get a tail var. And again, I've done 9 here because we selected N as the number, N equals 10 as the number of slices. Then the average of those becomes an estimate of expected shortfall. And I would emphasize here, because I know this has also been a point of confusion, that this is not a strict implementation here of this integral, of course. This is just an approximation. And what happens is, and it's only n equals 10 slices. As we increase the number of slices, we would expect to converge toward that true value. And that'll be true. I'll show you that in the R code because it's just much easier to use R code if we want to vary the number of slices in the tail. So table 3.2, my recreation from Dowd, simply shows that as we increase the number of slices, the expected shortfall increases toward that true value here, which we actually do because it's normal. We have a convenient, elegant analytical expression for. Table 3.3, now I'm changing a little bit because the previous 2 tails, again, were expected shortfall. And now we're stepping back to using that general risk measure where Dowd uses a different risk aversion function, right? In an expected shortfall, the risk aversion function is very simple. 0 weight to everything not in the lost tail, and then equal weighting to everything in the lost tail. Now, Dowd uses here an exponential risk aversion function, which is increasing as we move to the right. And in this case, then we do use the full distribution because this function here, conveniently, gives 0 weight to everything on the left, which in this case would be actually a gain, and then just starts to increase, you can see, very greatly. And here we only get to 90%, so it gets much, much higher as we get closer to the extreme tail. And now we take the same quantile, or what I call the normal deviate here, we weight it, take the product of those, and then the average of those is the risk measure here. So this is a general risk measure where we've defined a specific risk aversion function. And table 3.4 in Dowd just shows how that number also converges on a so-called true value as we increase the number of slices. But I also put that in the code. So now I'm going to shift to showing you these all of what I've just shown you here, but in R code, where it's actually much more flexible to vary things like the number of slices and the risk aversion function. So I start by loading the tidyverse, and then I'm going to define slices, and I'll set that to a low number just for the first run, only 10 slices, and then my confidence level, the variable will be con for that, will be 95%, pretty typical, and my significance level, as usual, will be 1 minus the confidence level. And then my increment here in the sequence will be the significance level divided by the number of slices. And then my sequence will be the variable SEQ. We'll use the sequence function that's built into R, which allows us to just define a vector as a sequence starting from some number. In this case, my starting number is going to be, let me get that little tag out of the way, will be my confidence level plus the increment, and then I'm going to go to the 1 minus the increment, and I'm going to go by the increment. So that command, pretty straightforward, starting from, going to, and by is the step along the way. And if I just run those, okay, then you'll see here my sequence. I'll just print my sequence out. You can see what I've done here. What I have is 9 values, right, as a function of slices is 10. We subtract 1, we'll get the number of values here, starting at 95.5% confidence, going in 0.5% increments, and ending at 99.5% confidence per the sequence command. And now the estimation of shortfall is just taking an average of the quantiles. So this ends up being really simple at this point because I can just use the Q norm command built into base R, or really stats R. If we want to take a look at that, I can do question mark here to get the help. Go over here, and you can see I get normal distribution. So I'm doing this procedure here with the normal distribution, but I have other parametric distributions available to me with equivalent commands. But you can see here with the Q norm here, what I'm getting is the quantile function. And all I need to do is provide here P, the probability, and my defaults will already be for a standard normal variable. So that I can take Q norm of this sequence, and what I get are, because sequence is a vector of those confidence levels, here I'm getting the associated vector of quantiles. And right here, so here's the quantile given the probability of 95.5%. That's that first one right here, 95.5% quantile right here. And my last one is 99.5%. That's the quantile. 2.58. That's a familiar quantile value because it corresponds to the Z value for a two-sided 99% confidence level. And here we have the 2.33 that is very familiar to us for a one-sided 99% confidence level. So we're getting the 9 quantiles here, and all that we need to do is take an average. Is how easy that command is, and we get 2.025 as the estimate for the expected shortfall given 10 slices. And so that corresponds to the value that's in Dowd's chart. But of course, 10 slices is not very many. We just need to increase the number of slices to get a better approximation. Well, and just by the way, just because I've been watching Matt Dancho taking his course, world-class programmer and teacher, uses the piping a lot, and that got me into the habit because this is not the first way I wrote this. If you like pipes, to me it's almost more natural to take that sequence and then pipe it to the Q norm function and then pipe that to mean. Just wanted to show you that that's the same, gets us the same result. Okay, so then what I'm going to do is just write an estimate function now, estimate ES, because what I'm going to do is I want to generate a table corresponding to Dowd's table that shows us this expected shortfall estimate for increasing values of slice, not just 10, but I want to increase that. So what I'm going to do here is take what I've just done and put it into a function so that I can reuse it for purposes of constructing a table. And that actually is pretty easy because I just need a function that's going to take slices and the desired confidence level. And all I'm going to do is copy the commands that I just did. I'll get that lined up. So pretty much a straight copy there, although I've just put it in a function that I'm calling estimate ES, per good style, trying to give the function name a verb as much as possible. Now I can call that estimate function. Let me just check, make sure it worked, or it shows up in the environment. And now just to test that, I can call that estimate function with, let's say, the same 10 slices, and 95% confidence level. Okay, it's working. And see, if I increase the number of slices to 100, then my value gets closer to the true value. And so what I'm going to do is create a slices vector. This is this is the table I'm going to create for, I'm going to run and I'm going to get the estimate, expected shortfall estimate for each value in this slices vector. And so I'm just going to go from 2 to 100 on that. And then I'm going to build the expected shortfall table, or Tibble is the tidyverse version of the data frame. And I'm going to use the per package with the very handy map function that's just incredible. And it's going to take the two arguments. The first one is my slices vector. Then I'm going to use a confidence level of 95, and then the function that I want to call, which is the function I just created. So here's the map to, and what this does for me, this is analogous to apply in base R. This allows me to call my function repeatedly for each value in this vector. It's really taking two arguments. So I'm calling my function the first time with 2 slices and the 95% confidence level. And then this map is, because this is a vector running from 2 to 100, it calls my function again with the next value, which is 3 slices, and then it recycles my second argument. See, it's mapped to, because there's 2 arguments. I'm calling the function with the 2 arguments repeatedly. Although this is a vector and this is just a scalar, so it recycles the 0.95 this way. So it'll call estimate expected shortfall again, and then it'll call it again with 4 and the same 0.95. So you can see here, I'm going to really call it, looks like 100 minus 2 is 98 plus 1. Looks like, I'm going to call estimate ES 99 times, once for each value in the slices vector, and then but the 0.95% will be recycled. And so that's going to construct basically the table for me if I run it. And let's just print it out. And you can see here we are. And in fact, so the first value here, that's the estimated expected shortfall with only 2 slices right here. 3, 4, 5, 6, 7, 8, 9, 10 slices. This is the same value I just ran the first time. That's taking the average of the tail sliced 10 times the average of those quantiles. But increasing all the way down to 100 that we can't see here, and we'll be getting closer and closer to the true value, which is in Dowd's table. He shows that as 2.0630. So you can see it's getting closer and closer to that. So what I'll do here is I'll just clean this up by converting that to a tibble. And then I'm going to bind a column, really add the column of my slices vector back to it. Whoops, so that I get now I put it back in a table. So now we're going to have the 99 rows here. Here's the estimate of expected shortfall for only 2 slices, not very accurate. And then we're getting the estimate as we increase the number of slices. Down here, getting much closer and closer to that true value, 2.063. And then, so finally, I can even just, it's set up, I put it in a tibble because then it's just so easy for me to plot it. If I want to give x the slices vector and Y is going to be the values, which are the only two columns in my tibble, so that I can plot points, and then I got a mistake, values not found. Oh, I guess that's value. Okay, and then we get a plot here of that estimate of expected shortfall moving to the right as we increase the number of tails, and this again is just for a 95% confident expected shortfall. So the last thing I'll do is just show you that spectral measure estimation, because again, what we just did here is estimated the 95% expected shortfall, which is a special case of that spectral measure. But if we want to generalize back to the spectral measure that Dowd shows, where he happens to use this exponential weighting function, so rather than just type that in real time, I've already defined that function, which again I got straight from Dowd, and is just simply a risk-weighted function. There's lots of different choices here, but if they're going to be coherent, or probably just in general, the key feature of the risk weight function is we want that risk weight to increase as the confidence level increases, right? We want it to be weakly increasing at a minimum. So I've defined that function here, and then with a gamma of 0.05, you can see my get weight function returns 0.33 at 80%. Okay, so then I'm going to do 100 slices, same command as before, dividing these slices, and then I'm going to set up the spectral table, not spectrum, spectral will be a tibble, right? I'll just start with that sequence vector that I just defined, right? So if we just look at that, very simple here, a one column tibble here. In this case, because I had 100 slices, it's going 1%, 2%, 3%. So these are the confidence levels. And when we have this general spectral risk measure here, we include the whole distribution, right? So we're starting at 0 with a 1% increment here, going all the way to 99%, because we happen to have 100 slices. So I'm going to take that tibble here, and I'm just going to add some columns with the mutate command, including the what I'm going to call nvar, which is that same command here where I retrieve the quantile really based on sequence, which will be in each individual instance will be the confidence level. So I get the nvar, and then I'm going to get the weight, call that weight, where I just call my get weight function, and it needs, you can see, two parameters, the confidence level, which is going to be in my sequence vector. So the first time we call it, it's going to be for the 1% confidence level. The second time we call it for the 2% confidence level. And I need a gamma parameter, which is just part of the get weight function, and it's not going to change here. It's going to be 0.05, and that's because I'm just using Dowd's example. And then I'm going to take the product of those, nvar multiplied by the weight, mutate. So cool, because I can do what's called lazy evaluation, right? I haven't even executed this, and I'm using the weight that I've just defined, right, the level above it. I think that's called lazy evaluation. And then my mutate is done. So if I do Control Enter and just run that, then let's take a look at my spectral table. And what I'm getting here is I didn't go to the trouble to format the weight, but I'm really getting here an expanded version of the same table that's in Dowd, and only I'm showing it for every single confidence level in 1% increments. But you can see here, At lower levels of confidence, you can see e to the negative 0.8 into engineering notation. These are essentially zero weights. And then we get up here and we'll get to some values that will match the values that are in Dowd's table. So here at 90% confidence, our weight here is going to be 2.7. You can see there's no, this value 0 here. So that is a raw 2.7. So the weights are basically 0 at the left tail and the body of the distribution, and then they start to increase as we get to the right tail. And so then we get some increasing weights. And then here I've taken the product here of the quantile and the weight, and which means that to get my spectral risk measure, all I need to do is average the values in my product column. So could have built that into my pipe, but here I'll just take spectral and pipe it to summarize the mean. No, sorry, summarize, I'll call it risk equals the mean of my product column. And I get 1.58, which does correspond to that value in Dowd's table where we have 100 slices. And so if you're bothered to stay with me so far, you probably know what I do next. I'm not going to retype it for you in real time because it's mostly I just copied it into a function called getSpectral. Again, trying to use a verb, good practice. And now I can call getSpectral for each value of the number of slices. If I go back to the 100, that's that same 1.58, but I can increase it to 1,000 slices and I get 1.819. So that's basically the execution of both the expected shortfall and the spectral measure in the R code. And I'll put the link here up to this code on a GitHub repository if you'd like to access the code. So if you found the video helpful, subscribe to the channel and you'll get to see my next video. Thank you.